In this review example, we're using all the electrostatics quantities that we've defined so far. So we're asked first about an electric field, and then an electric force, then an electric potential, and finally an electric potential energy. So when I look at my picture, I have a positive charge here shown in red, a negative charge of -1 microcoulomb, 1 meter above that red one, and then we have a point of interest marked exactly to the right of the red one by 50 centimeters. So the first question is, find the electric field at that point of interest in polar form. So that means we want a magnitude and direction of that electric field. So before I start doing anything, just qualitatively, this positive charge is going to contribute a rightward component of the electric field, and my negative charge is going to contribute a component of the electric field that's weaker, so I drew it shorter. This is because the two source charges have the same magnitude, but our point of interest is farther away from the negative charge. And this component points partly up and partly to the left because it has to point exactly at that negative charge. I'm going to call that piece E minus, and as you might suspect, the component due to the positive charge will be called E plus. So I've got to get the magnitudes of each of these pieces, and then to do the vector addition of these electric field vectors, I have to break into X and Y components, add the components, and then express the final result in polar form. Just completing that triangle real quick, what I want to get right now is the separation distance between that negative charge and the point of interest. And that's given by the Pythagorean theorem. It's going to be the square root of the sum of the squares of the legs. So that's 1 squared plus 0.5 squared. And when I do that, I get 1.12 meters. Now I can find the magnitude of E minus. It's going to be KQ over R squared. That K is the Coulomb's law constant, 8.99 times 10 to the 9. The charge is -1 microcoulomb. It doesn't even matter if I keep the minus sign here as long as I'm faithful to my picture. I'm just going to work in magnitudes. A microcoulomb is 10 to the -6th. And just so I don't get too much rounding error, I'm going to go back here and say R squared would be 1 squared plus 0.5 squared. That's 1.25 exactly. So I'm dividing by 1.25 exactly. And so it turns out E minus is 7,192 newtons per coulomb. Now let's get E plus. That's KQ over R squared, 8.99 times 10 to the 9, 1 microcoulomb, all divided by 0.5 squared. And when I crunch these numbers, I get a much stronger field contribution of 35,960 newtons per coulomb. Okay, next I'm going to work on breaking E minus into vertical and horizontal components. So I need that angle theta. And I'll go ahead and put that here since space is so limited in this problem. Theta is the angle whose tangent is 1 meter over 0.5 meters. And when I run the numbers on this, I get 63.4 degrees. Now I can break E minus into components. So I have E minus X component. I'll just draw these components real quick. There's E minus X component and E minus Y component. The X will be given by the cosine and the Y by the sine. So E minus X component is going to be E minus cosine 63.4 degrees. In other words, 7,192 newtons per coulomb, cosine 63.4. And this points to the left, so I'll keep track of that with a minus sign. Negative 3,220 newtons per coulomb. The Y component of E minus, that's E minus sine 63.4. That's 7,192 sine 63.4. And that gives me 6,431 newtons per coulomb. Finally, I want to get my total X. So I'm just going to call that EX. And that's E plus. That was a rightward pointing contribution from that positive charge, 35,960 newtons per coulomb, minus the 3,220 leftward component of the second contribution from the negative charge. So my total X component is 32,740 newtons per coulomb. My total Y, well, I only have one contributor to that, it's that piece of E minus, is 6,431 newtons per coulomb. And now I have the total X and Y components of this vector, and I'm almost ready to put it into polar form. So to finish with the polar form calculation, I draw a triangle. My Y component is 6,431 newtons per coulomb. My total X component, 32,740 newtons per coulomb. I want to know the angle that this points at, and I want to know the total magnitude of E. So I'll have to steal a little space from part D here, but I get E is the square root of the sum of the squares of the legs, so 32,740 squared plus 6,431 squared. When I run the numbers on this, I get 33,400 newtons per coulomb. Again, using the convention of rounding to 3 sig figs unless otherwise indicated. Then the angle for my net electric field is the angle whose tangent is 6,431 over 32,740. And I get 11.1 degrees out of that. All right, that's quite a bit of work doing all that vector addition stuff. The rest of the questions are a lot faster. So in part B, I want the electric force on a 0.1 microcoulomb charge placed at X. And I already have the magnitude of the electric field. I'm assuming this question is asking for the magnitude of the electric force. But if we wanted direction as well, you would just tack on that 11.1 degrees north of east. So let's just get a magnitude. And the magnitude of the electric force is just the size of the charge multiplied by the magnitude of the electric field. So 0.1 microcoulombs, a microcoulomb is a millionth of a coulomb, multiplied by my electric field, which is 33,400 newtons per coulomb. I skipped the units there, but they come out to newtons. And I get 0.00334 newtons, or if you want, you could be clever and put it in millinewtons, but that's kind of a goofy unit. In part C, I'm asked for the electric potential at X, using the fact that electric potentials from multiple sources simply add to each other. So I'm going to have a contribution at X from each of these point charges, and I'll call them V minus and V plus. All right, electric potential is just KQ over R. So I have 8.99 times 10 to the 9 for the Coulomb's law constant, and then my negative charge was 10 to the negative 6th coulombs, and then my distance to the point of interest was 1.12 meters. And I get a negative potential contribution from that negative charge, and that's negative 8,027 volts. Then I look at the contribution from the positive charge. That'll be KQ plus over R plus. So 8.99 times 10 to the 9. The charge was positive 1 microcoulomb, and the distance to the point of interest was 0.5 meters. And I get plus 17,980 volts. If I add these two quantities, I get that the total potential at the point of interest is 9,950 volts. Finally, in part D, we're asked for the electric potential energy contribution due to the presence of the 0.1 microcoulomb charge placed at the point of interest. Now that wording may seem a little bit curious to you, but what I'm trying to defend against here is the fact that there's also a potential energy contribution due to the interaction between the two source charges. So there's a big chunk of energy there, but we found the total potential now at the point of interest, and that takes into account the energy contribution of the charge sitting at that point due to both the positive and negative source charges. So it's just the potential energy of that test charge that we put in the mix, not the total potential energy of the three charge configuration. Once you have the potential, this is very fast. The potential energy is just QV. So 0.1 times 10 to the negative 6 multiplied by 9,950 volts, and I get 0.000995 joules. At this point, there's probably too many zeros to keep hanging around, so that's 9.95 times 10 to the negative fourth joules. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.